All right, today we are going to kind of finish up our conversation a little bit on how we want to go about factoring, and then also a little bit about how we can use factoring to actually solve some quadratic equations. So what we're looking at here is we're going to solve by graphing and factoring. We've already talked about graphing. Basically what we're going to do is we're going to use the whole graphing idea to kind of show what we're finding when we're actually solving these using factoring. And then we're going to talk about what it means to find roots, and then use those roots to kind of work backwards to find what the original quadratic function would be. All right, so these are some terms that you're going to hear me talk about quite a bit as we go through this. The zero of a function and the root of a function basically mean the exact same thing. What we're looking at with both of those is the zero and the root are basically the solutions to the quadratic equations we're going to solve. And what we're going to come to look at here is when we have a parabola, when we're solving this, so we're finding the roots or the zeros are just the places where that parabola crosses the x-axis. Okay, and we'll get into a little bit more of that later. Another couple terms here, and we've kind of maybe talked about these a little bit already. Binomial and trinomial. Bi just means two, so it's going to be a quadratic equation or function that only has two terms. A trinomial, tri meaning three, is going to be a quadratic equation, quadratic function that has three terms. All right, now I kind of alluded to this a little bit on the previous slide, but we'll kind of clear up a little bit of what we're talking about again. So the zero of a function, or basically the root of a function, is exactly what this picture down here in the bottom right-hand corner of the screen is talking about. Okay, the zeros we're finding are the points at which the graph is going to cross the x-axis. Okay, the x-coordinates of those 2 points would be our zeros. So basically what we're looking at here is when we solve this, we're looking for the x's that I can fill in to a particular quadratic function. Okay, what can I put in for these x values that is going to make my output value, okay, equal to 0. Okay, so if you think about it, right here I'm going to have some x value and my y is 0. Same thing over here. At this point I have some x value and my y is 0. So if my y is supposed to be 0 at both of those points, essentially I'm going to put 0 in this spot right here, and I'm going to kind of work backwards, and we're going to use some factoring to figure out what those x's would have to be in order for that function to give me an output value of 0. Okay, now in most cases when we solve these and factor them, we're going to end up with 2 zeros, or basically 2 solutions. There are certain cases where your parabola may only have the top or the bottom portion touch the x-axis. In that case, it's going to look like you're going to get 2 roots or 2 solutions, 2 zeros, but really both factored expressions are going to give you the same 0. So you're only going to get 1, and that would make sense because we're only intersecting or touching the x-axis in one spot. And we'll talk a little bit more about those as we go. Okay. This is basically just saying that any point on a parabola, we're symmetrical here, splitting it in half. If I have a point over here that has the same y value as a point over here, those are basically supposed to be about the same distance from that axis of symmetry, or the center of that graph. Okay, so just kind of a little reminder there, and kind of builds upon what we talked about before. All right, now we're going to start with graphing. We're not going to spend a lot of time graphing. We want to get into the factoring and how we can use factoring to solve these. But the first thing I'm going to do is I'm going to go ahead and graph a function, and again we're just going to talk about what the solutions would be if we're actually solving this. So I'm going to use some of the stuff from the previous two sections. First thing I want to do is I probably want to figure out what my vertex point is going to be. So I'm going to go x equals negative b, which in this case would be 6, over 2 times a, which would be 2 times 1, and get 3. Okay, so we know that's the x coordinate of my vertex. Now I'm going to take that and I'm going to fill it in to the original equation. So 3 squared minus 6 times 3 plus 8. Alright, so I'm going to end up with 9 minus 18 plus 8. Alright, so essentially 17 minus 18, so it's going to give me negative 1. Alright, so I filled in 3, I got negative 1, so my vertex is going to be somewhere right about in this area. Okay, we can take a look at this a little bit like we did before. This number up here, like we talked about in the previous section, is my y-intercept. So I know I'm going to cross the y-axis over there. Now I'm going to draw in kind of my axis of symmetry here, so I can kind of see spatially here where I might be able to put the point that corresponds or reflects to that right there. Now, what we're really looking for here when we're graphing this is places where the graph is going to intersect the x-axis, because basically that's what my my solution points are going to be here. Now, I can't be 100% sure what they're going to be by graphing, and that's why we don't usually use graphing to find this a whole lot, just because it can be kind of a guess and check. We have to fill stuff in all the time. But what I'm going to do is I'm just going to take an x value of 4, which would be kind of my next x value to the right here, and I'm going to fill that in, because it looks like if my parabola is going to go up, that should be relatively close to where it's going to cross the x-axis. So 4 squared minus 6 times 4 plus 8. So 4 squared is 16 minus 24 plus 8. Alright, well it looks like I got lucky, because 16 and 8 is going to give me positive 24. So that's going to equal 0. So I put in 4, I got 0, and I can put that on the other side. So right here we can see that the two places where I cross the x-axis are going to be when x equals 2 and when x equals 4, based on the two circles where the graph crosses the x-axis. So in this case, if you were being asked to find the zeros would be x equals 2 and x equals 4. Alright, those two values are what give you an output value of 0. So again, if you take 2 or you take 4 and you fill it into the original equation that's up here, the output value that you get is going to be 0. Therefore, you have the point 20 and the point 40, which are shown by my dots on the graph over here. Those would be the 2 points where my graph crosses the x-axis. Therefore, those are my 2 zeros, or my 2 solutions for this particular quadratic function. Alright, now graphing, like I said, can kind of be a pain because it's kind of a guess and check deal. So what we're going to do is we're going to talk about how we can take factoring and how we can kind of link it to what we've been doing the last few days, okay, and see how we can find the roots, or basically the zeros of an equation. Okay, the process is fairly easy. Alright, if you're given a function like this and we're actually asked to find the roots, okay, we're going to factor, but what we have to do is we always have to set our equation equal to 0. So you need to have all your terms on one side, and on the other side you need to have 0. Now the whole idea here is we're trying to find the x values that give us 0, or an output value of 0. So that's why I want to get everything on one side, and as far as my terms are concerned, and have 0 on the other side. Okay, so what we're looking at here is when we solve these functions, our zeros are going to be our x-intercepts, which we talked about already. The points where I intersect the x-axis, those are my solutions. Okay? They can be referred to as zeros, they can be referred to as solutions, or they can be referred to as roots. So in any case, if you were asked to find the solution, find the zeros, or find the roots of a quadratic function, you're going to factor and you're going to solve, at least factor for right now. We'll talk more about different rules or different methods for solving this as we go. So all we're going to do is we're going to take the function that's given here for us, and I'm going to kind of flip things around, but basically in place of this f of x, I'm going to put a 0, because what we want is an output value of 0. Now I'm going to try to factor. Okay, now I encourage you to kind of write down and take notes on what I'm doing right here. I'm not going to have as many examples throughout the video for you to work on as I typically do, simply because we've talked about factoring in class already, so I don't want to make this video longer than it needs to be. Alright, so if I factor, I'm going to look to see if they have anything in common, which they do not, so I can't factor anything out right away. So I'm going to go straight to my two sets of parentheses. I'm going to leave it set equal to 0. So the first spot, x and x are what give me x squared. I know my signs are going to be different because of this sign back here. Now I need factors of 12 that could basically give me a difference of -4. So I'm looking at 6 and 2. So just to check, this would give me -6x, this would give me +2x, which in the end is going to give me a difference of -4x. So I'm factored. Now as far as what we did in class, that's where we stopped. Alright, but if we're going to solve, what we actually need to do is take each factored part, each thing that's in parentheses, and we need to set those each equal to 0. Alright, then what I'm going to do is I'm actually going to solve for x. Alright, so over here I would subtract 2, so x is going to equal -2. And here I would add 6, so x is going to equal 6. So in this case, these would be the zeros of the function. If you were to go ahead and fill these back into the original equation, you would get an output value of 0. Okay? So really all we've done with the factoring process, as we've taken our factored part and we've simply taken it a step further. Okay? So not really a whole lot new there. That's why I'm not going to put a ton of examples in there. Alright? But we're just kind of building on what we talked about in class already. So again, your final answers would be -2 and 6. Alright, and those would be the x values or the x coordinates to where this parabola, if we were to graph it, would cross the x-axis. Alright, here's another example. As opposed to the one before, which we would refer to as a trinomial, this is a binomial. You see there's only 2 terms. Alright, same thought process. I'm going to take the function I'm given, I'm going to set it equal to 0. I want to know what values of x are going to give me an output value of 0. So this one, again, we know that we're not going to have 2 sets of parentheses because there's only 2 terms. So the only thing I can look at here is, what do those 2 terms have in common? They can both be divided by 3, and they can actually both be divided by x. Alright, so if I do that, I will end up with x plus 6 left over in parentheses there. Now, a little bit different setup here, but we still have to take the 2 separate parts here, the 3x, and set it equal to 0, and the x plus 6, and set it equal to 0. Now, this one over here, this part, is relatively easy because there's only one thing that I could fill in for x and multiply by 3 that's going to give me 0, and that's going to be 0. Over here, if we subtract the 6, x is going to be -6. So again, x equals 0 and x equals -6 are the roots or the zeros of this particular quadratic function. Alright, now something to keep in mind here a little bit as you go through this. Had this just been, well, say for example in this spot right here, say you could only take out a 3 and not an x. So I'll just give you a different example here. Say this is what you ended up with as far as your factor is concerned. you don't have to take this first part and set it equal to 0 if there's no variable in there, because all you would get is 3 equal to 0, and that doesn't make any sense. Alright, so in this case, I would just set the x plus 6 equal to 0, get my answer of -6, and I would only have 1 0 for that function if there was no variable out front over there. Okay, so that would be a case where your parabola, the vertex, is probably right on the x-axis somewhere. Alright, so just something to keep in mind. If there's a variable out front, you have to take and set it equal to 0 like we did over here, both parts. If there's no variable, just a number, alright, then we're only worried about the part that has the variable, setting that equal to 0. Alright, now a little bit of story problem, word problem type stuff here. What you're going to want to do on your notes is you're going to want to keep track of what all of this means right here. Okay, all it is a quadratic function that's used to basically represent or model projectile motion. Okay, the -16, this value and this value are constants, or something that's going to be given to you in the problem. I shouldn't say constant. This part here is a constant. It's always going to be -16 in front of your t squared. Okay, this number that goes in here in front of the t is going to be whatever your initial velocity is based on the problem. This number right here is going to be whatever your initial height is. Now I'm basically going to tell you, for the most part, in a lot of these projectile motion problems, it's going to say that your height is going to start, at ground level, so we can most of the time fill in a 0 for that particular function. So just remember, initial velocity goes in here, initial height goes in here, the -16 is constant, so that's always going to be a part of your problem. Okay, on the bottom here, just something interesting to note, and this is kind of a physics side of things, but this is supposed to represent the height that something goes after a certain amount of time. That's what h of t means, height after a certain amount of time. This formula does not account for air resistance, wind, and other real-world factors. So this is kind of theoretical, and when you get into physics, you'll notice that's something that we talk about a lot, is how do things work theoretically. Okay, so what I'm looking at here is a golf ball is hit from ground level, so ground level right away. That's kind of a dead giveaway that my initial height is 0. Okay, we have an initial velocity of 80 feet per second. Okay, after how many seconds will the ball hit the ground? Now, don't make this harder than it has to be. We've been working on solving by factoring, so we're going to solve this by factoring. So I'm looking at the equation from the previous slide, -16t squared. My initial velocity is going to be 80, so I'm going to have 80t, and it said my initial height was 0, so technically I would have a plus 0 at the end. Well, you don't have to write plus 0 at the end. So I'm going to take this equation, just like we did before, this function I should say, and I'm going to set it equal to 0. Okay, now this is very similar in nature to the problem that we just looked at in the previous slide, or a couple slides ago, where we were factoring something out. Okay, you will notice that 80 and 16 are both divisible by 4, and I'm pretty sure they're both divisible by 8. So if we divide them both by 8, actually 80 might even be divisible by 16. It is. That makes things a lot easier. So I'm actually going to factor out a -16 and a t for everything, because they have a -16t in common. So t, now remember we took out a negative here, alright, so it's going to actually change my sign. It's going to look like that. Okay, so I took out a -16t, 16 goes into 80 5 times, so I get that -5 in there. Alright, now again, just like before, I'm take both parts, and I'm going to set them equal to 0. Alright, so again over here, if it's just a number and the variable equal to 0, we know t has to be 0. And here if we add the 5, t is going to equal 5. So after how many seconds will the ball hit the ground? Well, technically at 0 seconds here, we'd be talking about what the initial height of the ball is. So it's going to be at ground level to start. So we don't really worry about that one so much. We're looking at this one more. All right. What that means is, if you think about this, ground level is right in here somewhere. Okay, at 0 seconds we're on the ground, and if we go up and over and down here, after 5 seconds, my golf ball in this case is going to hit the ground. Okay, so again, don't get too caught up in worrying about, oh my gosh, it's a word problem. Just think, hey, we've been factoring, so that means we're probably going to have to factor to solve this problem as well. All right, now this is just a graph from a graphing calculator that shows us, again, kind of what I drew on the previous slide, showing that we have 0 values at 0 and then again after 5. Okay, and again, the only one that we're really worried about is this one down here, because that represents the end flight of my golf ball. Now, there's a couple special ways to factor that we didn't talk about in class, and to be honest with you, I really only worry about the difference of squares. This one over here, the perfect square trinomial stuff, if you know how to do that based on the pattern, that's great. But if you can't pick it out of something, you can just factor regularly and still be able to figure that out. The key with the perfect square trinomial is when you're done, you're going to have the same thing in each set of parentheses after you factor, so you can actually write them as a square of a binomial. So when you factor, if you get x minus 2 and x minus 2 as your answer, okay, what you can do with those is you can actually just write the factored solution as x minus 2 squared. All right, and you can see with something like this, if you were to set each of those parts equal to 0 and solve, you're going to get the same answer for each part. Now you don't have to write that answer twice, and in this case your answer would just be x equals 2, and all that's saying for you is that your parabola is only going to intersect the x-axis in one spot or at one point, and that's going to be where x equals 2. Again, I'm far more concerned with the difference of squares. It's going to be one of the few times where you factor something that only has 2 terms, and you don't necessarily have to take something out or factor something out to begin with. All right, so if you have 2 terms and there's a minus between them, you basically just want to look and see, is the first term and the second term both perfect squares? If they are, we know it's a difference of squares. And like I said, you're going to want to get to the point where you get pretty good at understanding what a perfect square or a difference of squares is. All right, so I'm going to approach this the same way I did before. Now what you will see about this is it's a little bit different. It's not written in function form. It's just written as an equation. Like we talked about before, if we're going to factor to solve these, we have to make sure that they're set equal to 0. Okay, written in standard form, set equal to 0. So standard form again meaning x squared, my x term, and then my constant if I have one. Okay, now what you'll notice here is this is a perfect square and this is a perfect square. All right, basically meaning I had to take 2x times 2x to get 4x squared, and I had to take 5 times 5 to get 25, and based on what the last slide told me, I just put opposite sides between them. Okay, now technically this should still be set equal to 0. Now because I have a number in front of the x here, what you're going to notice is if I add 5 over here, 2x is going to equal 5, and over here 2x is going to equal negative 5. I'm going to end up with fractions as answers. That's fine. So in this case, I'm going to have x equals 5 over 2 and x equals negative 5 over 2. All right, just leave them as improper fractions. Don't spend your time trying to think about, okay, this is 2.5 and that's negative 2.5, something like that. Just leave them like this. That's perfectly fine. That's the way I leave most of mine when I go ahead and solve it. All right, so again, what this would mean for us is my graph is going to intersect the x-axis at negative 5/2 or negative 2.5 and positive 2.5. Okay? So, just like I said, example of difference of squares. All right? Other examples of difference of squares, and typically they're a little bit easier, but if you have something like x squared minus 9 or x squared minus 16, something like that, x squared minus 25, all right, you can kind of start to see the pattern. Okay? First term is a perfect square, second term is a perfect square. So I can write it as a difference of squares. All right, so going back there, it's just a good thing that you take notes on what the formula for the difference of squares is, because as we move forward, you're really going to want to understand that so you can pick it out. It makes things a lot easier. All right, here's another example. I'm going to tell you right away, this is going to be a perfect square trinomial. I'm not going to factor it out based on what the formula for that tells me. I'm just going to factor it out like I normally do because I think it's easier, just as easy to understand what's going on this way than it is to try to fill it into a formula. Now what I'm going to do is I have to take and move these two terms over to this side. Now the reason I move those two over as opposed to subtracting the 18x squared is because I really don't like this first term here to be negative. It's much easier if it's positive. Okay? Now, what I'm looking at here again is, do they have anything in common that I can factor out right away? And in this case, it looks like I should at least have some numbers in common. Looks like I'm just going to start with a 2, and if we can take out more than 2, we will. So that leaves me with 9x squared minus 24x plus 16. And that's supposed to be equal to 0. All right. So again, it looks like I got everything out that I needed to there. Okay. So now I'm going to go straight to my two sets of parentheses here. Okay. Now there's a couple different ways we can get 9x squared. I'm probably just going to go with 3x and 3x because, like I said from the beginning, if it's a perfect square trinomial, that means you should be able to write it as a square of a binomial as we go here. My signs are both going to be negative because they're both whatever that is. And I'm probably looking at 4 and 4 here. So just to check, this is giving me negative 12x. Negative 12x gives me the negative 24 I'm looking for here. All right, now if we're solving this, all right, again, because I have the exact same thing in both sets of parentheses, I only have to do this once, because if I set them both equal to 0, I'm going to get the same answer either way. And I do not have to set this 2 equal to 0 because there's no variable with it. All right, so in this case, I'm only going to get one answer. All right, and that answer is going to be x equals 4/3. All right, so again, this middle part here, I can write it like this once it's factored because I have the same thing in each set of parentheses. So technically, we could have wrote the factored version of that like that. But basically, all this is telling you right here is you have the exact same thing in both sets of parentheses. So you only need to set it equal to 0 once, and you're only going to get one answer. All right. Now, hopefully you've taken some notes so far to this point so you can kind of refer back to them. Again, all we're doing is taking the factoring process one step further, and we're using it to solve. Now, this next part is the last part of the assignment, but what it does is it's going to start by telling us what the zeros or the roots of a function are, and we are supposed to work backwards to figure out what the original rule or the original function would be if that's the case. So I'm going to kind of start down here, and I'm going to think about it like this. If my final answers are supposed to be x equals 4 and x equals -7, that means that in my parentheses here, and you've probably kind of noticed this as we go through here, if I'm supposed to get an answer of x equals 4, that means I probably had x minus 4 in here, and I probably had x plus 7 in here. Okay, again, if I'm taking these parts in parentheses and setting them equal to 0, that means that I would probably end up getting these as answers down here. Alright, so now to work backwards, we just have to FOIL. So x and x gives me x squared. X and 7 gives me plus 7x. This gives me minus 4x. This gives me minus 28. Alright, so x squared plus 3x minus 28 would be the original function. Okay, and technically we could probably put an f of x out front. Alright, quadratic function that would have zeros of 4 and negative 7. Okay, so again, just working backwards, kind of understanding how we go from the factored part to getting our answers is a big part of how we figure out what's going on here. Okay, again, here's another example. If we have zeros of 5 and negative 5, alright, if we're going to work backwards from this, alright, if it says positive 5 down here, that means I must have had x minus 5, and I would have had to have x plus 5 over here. Now, this factored part basically looks like a difference of squares, which I can tell you right away would mean that you started with a function that looks like this. But we'll FOIL just to double check. So x squared is going to be plus 5x when I do this part, minus 5x when I do that part, minus 25 at the end. And you can see in the middle here, these are going to cancel each other out. So my function does become x squared minus 25. Alright, now the last thing here, this is basically saying that you can have multiple functions. We have 3 of them up here, and all of them happen to have the same zeros. Now you can notice from the graph down here that not all of them are the exact same parabola. Some of them are skinnier, some of them are narrow, some of them open down as opposed to opening up, but they all intersect the x-axis in the same spots. So what that says for us is basically the fact that zeros can be common between different quadratic functions. Alright, so hopefully you had the opportunity to get some notes taken here and make some connections as far as what we talked about in class based on what I'm expecting you to get out of this particular homework assignment. Okay, if you have questions, please make sure that you come in to ask. Otherwise, the notes are due next class period, and try to get a good start on your homework here so we can kind of see what kind of progress we're making next time we meet.